Hi there, Mr. Sutton here, bringing you the BC Calculus 518 Part 1 homework solutions on improper integrals. On this problem, I want the integral from 2 to infinity of dx over x squared. Because this is an improper integral with that infinity in there, I'm going to set this up as a limit. So limit as b approaches infinity of integral from 2 to b, and we'll have x to the negative 2 just so I can anti-differentiate a little easier here. Now that I've set it up like this so that I'm approaching infinity rather than trying to plug it in directly, let me take my antiderivative. That bumps up to a negative 1. Dividing by that, we've got negative x to the negative 1, evaluated from 2 to b. And I'll just save myself a little bit of time and write that as negative 1 over x. So plugging things in now, I've got negative 1 over b plus 1 over 2. It would have been minus, but we already had a negative built in there. As b approaches infinity, this is bottom heavy and goes to 0. So I essentially have 0 plus 1/2, which is 1/2. Choice A. For this one, we want the integral from negative 1 to 1 of 3 over x squared. Now, before you go ahead and turn this into 3x to the negative 2 and use a reverse power rule, keep in mind there is a discontinuity at x equals 0. 3 over 0 squared, that's no good. So because of that discontinuity at x equals 0, we have an improper integral, and we actually have to break this up using some limits in order to properly evaluate it. So I'm going to have a limit as we're approaching 0 from the left side, from negative 1 to 0, and I'm also going to have a limit of the integral as we approach 0 from the right side, from 0 to positive 1. Writing that out, I have the limit as b approaches 0 from the left of negative 1 to b of my function here. And I'm adding to that the limit as a approaches 0 from the right side to 1, and we've got 3x to the negative 2 in that as well. And notice I changed this into the negative 2 like I set up here, because I am going to use my reverse power rule. I just want to make sure that I don't just kind of gloss over this discontinuity. All right, using my reverse power rule safely inside my limit notation here, this bumps up to a negative 1, so this is negative 3x to the negative 1, evaluated from negative 1 to b. Still have this limit hanging around. Over here, same antiderivative, different limit though. A is approaching 0 from the right. A to 1 is our limits. And before I go ahead and plug in all of this stuff, at some point you're going to have to plug b in here. When you take the limit as b approaches 0 from the left, or either side, of negative 3 over x, or negative 3 over b in this case, well, you're essentially just dividing by 0, which is a limit that does not exist. Since this little piece of everything does not exist, the whole integral diverges, and we have to pick choice E on this one. For this one, I'm trying to find the integral from 4 to infinity of this crazy-looking rational radical expression. Since I've got an infinite limit of integration, I'm going to set this up as a limit on the outside. So I'll do the limit as b approaches infinity of integral from 4 to b of all this stuff. That just makes it a little bit more legal so that I'm approaching infinity instead of plugging it in. And now I have to actually integrate this. Since I see a function, an inner function, and its derivative in the same problem, I'm going to try to use substitution. I'll let my u value be 9 minus x squared. So then du is going to be negative 2x dx. And I can rewrite dx as du over negative 2x while I'm at it. Now I need some u values. If x is 4, then 9 minus 4 squared gives me a u value of negative 7. And if x is b, then we've got 9 minus b squared. Okay, plug in all this in. We still have limit as b approaches infinity, but now we're doing the integral from negative 7 to 9 minus b squared. We've got negative 2x over the cube root of u. And then over here, dx is being replaced by du over negative 2x. So those negative 2x's actually cancel out completely, which is awesome. And I'm going to rewrite my u with an exponent of negative 1/3. And now it's time to actually take the antiderivative of u. So that bumps up to a power of 2/3. Multiplying by the reciprocal of 3/2, we have 3/2 u to the 2/3, still evaluated from negative 7 to 9 minus b squared as b approaches infinity. And at this point, it's time to plug stuff in. So I'm going to yank that 3/2 out, and the stuff inside is kind of a mess. Anything I'm plugging into u, I'm taking the cube root of and then squaring it. So I've got all this stuff inside a cube root and squared. And then minus, we've got -7 getting the same treatment, cube rooted and squared. So as b approaches infinity, we're doing essentially 9 minus infinity, which is going to give you something infinitely negative. If you square that, if you cube root that, that's still something that's infinitely negative. And then if you square that, it's infinitely positive. This all comes out to infinity. So the limit does not exist on this, which means that our integral diverges, and choice E is our answer. For this one, we want the integral from 1 to infinity of this expression. Since I have an improper integral with an infinite limit of integration, I'm going to set this up as a limit. So my limit will be the limit as b approaches infinity, integral of 1 to b of all this stuff. And now let me actually integrate this. So I have an inner function here, and its derivative. This looks like u substitution. So let me let u equal x cubed plus 2. And then du is 3x squared dx. Dividing by 3x squared, we have dx equals du over that. And for u values, if x equals 1, then we have a u value of 1 cubed plus 2, so that's 3. And if we have an x value of b, well, that's a little bit easier, then we just have b cubed plus 2. All right, substituting back in, we have limit as b approaches infinity, integral from, we said 3 to b cubed plus 2. In here, we've got x squared over u squared, and then dx is being swapped out for du over 3x squared. X squareds cancel. We've still got a 3 down there, so this is 1/3 u to the -2. And now let me use my reverse power rule. This bumps up to a -1, so this is -1/3 u to the -1 from 3 to b cubed plus 2 as b approaches infinity. A lot of stuff to keep track of at this point. All right, time to plug stuff in. I'm going to yank out this -3. And inside now, I've got u to the -1, so that's going to be 1 over b cubed plus 2 minus 1 over 3. As b approaches infinity, this first term is bottom heavy, so it goes to 0. I've got -1/3 times 0 minus 1/3. So this is -1/3 times -1/3, which is 1/9. Choice B. For this problem, we're trying to find the integral from -1 to 2 of the absolute value of x over x dx. Now, you've probably seen this crazy-looking function before. You might remember this is the one that's like 2 horizontal lines, but with a big jump in between them. So clearly, we have a discontinuity here. And, of course, it's at 0, which naturally is inside our limits of integration. This discontinuity at 0 gives us an improper integral. So to properly evaluate this, we need to turn it into some limits coming from the left and the right as we approach 0. All right, before I can do that, though, let me actually rewrite this as a piecewise function because it's kind of hard to take any limits of this thing without expressing it as a piecewise. So I'm going to let all this be represented by f of x just so I don't have to keep rewriting it. And that's going to equal the following piecewise. So we're going to have a border value of 0. So I have a rule for if x is less than 0 and if x is greater than 0. If x is less than 0, then I have to force the stuff inside here to be positive. That's what absolute value does. So my rule is going to be -x over x. If x is already greater than 0, then absolute value can just kind of sit back and let reality take its course here. That's just going to be x over x. We can just drop absolute value if x is already going to be positive. And to make my life even easier, I'm going to simplify this to -1 and 1, just getting rid of those holes so I don't have to bother doing it later. All right, so now expressing this integral with some limits, we're going to have the limit as b approaches 0 from the left of -1 to b of f of x dx. And we are adding to that the limit as a approaches 0 from the right of integral of a to 2. So this takes care of everything from -1 to 0. This one is handling everything from 0 to 2. And we're not actually plugging in 0, we're just approaching it. All right, so we need antiderivatives. Here's the antiderivative for this first rule here, the stuff that's less than 0. Antiderivative of -1 is negative x. So there's all that stuff. Limit as b approaches 0 from the left. And over here we need the antiderivative of 1. This is the second rule we're using now. That's going to be x evaluated from a to 2. Plug in stuff in. Over here we've got negative b, and then let's see, we're doing a lot of minuses. So we've got 3 minuses actually. You have the negative here, we have the negative in the -1, and we have the fact that you're supposed to subtract when you're doing this evaluation box. 3 negatives gives us a -1 when all is said and done. Over here now, this is a little easier. We just have 2 minus a. And now it's time to actually plug stuff in. If we plug in 0 or approach 0 from the left here, this is just 0, so we have a -1 for this first limit. Over here, if we approach 0, we've got 2, because 2 minus 0 is 2. And then -1 plus 2, don't mess it up now, that's going to be 1, which gives us choice B. On this problem, g is twice differentiable. G of 1 equals 0.5, and the limit as x approaches infinity of g of x is 4. Based off of this, we want the integral from 1 to infinity of g prime of x dx. This is an improper integral since we're going to infinity, so I'm going to rewrite this with a limit as b approaches infinity of 1 to b of g prime of x dx. And now I'm just going to go ahead and integrate it like I normally would. Antiderivative of g prime, of course, is g, so I'm evaluating g from 1 to b with b approaching infinity. So I can write this as g of b minus g of 1. And there's a few things I can do at this point. As b approaches infinity, we're using this piece of information up here. Here they said that when your input's approaching infinity, the g function goes to 4. So this first piece, g of b with b to infinity, is 4. And then this other one, g of 1, well, they actually gave that to us. They said g of 1 is 0.5. And we know that the limit is going to be 0.5 as well, because they said it was a twice differentiable function, which means that it's definitely continuous, which means function values and limit values, the limit as x approaches 1 of g is also going to be 0.5. So this is 4 minus 0.5 then, which is 3.5, giving us choice B.